Lesson 6, pH regulation in the stomach. So here we have the understandings, what you are expected to know. And then we have your applications, how we're going to take what we know and what you're going to be able to do with that information. So the first thing we have to talk about is your gut, which is also known as your gastrointestinal tract. Well, it generates and maintains different pH environments along its length, which plays an important role in controlling the activity of digestive enzymes. Okay, so the pH in our gastrointestinal tract plays a very big role in enzymes that we have in our body. So you should remember that the pH in the stomach is very low. It is between 1 and 2 owing to the production of hydrochloric acid by the millions of parietal cells that line the stomach. The stomach is maintained at such a low pH for two main reasons. So the acidic environment is not tolerated by the majority of microorganisms, we're talking about bacteria, that may enter the digestive system with food. So if we have a low pH, that is how our body acts as its natural defense against disease-causing bacteria, other disease-causing microorganisms. The digestive enzymes in the stomach, okay, an example includes pepsin, which breaks down proteins in the food that we eat, requires a low pH for optimum catalytic activity. So as we can see, there's a twofold reason that we have a really acidic environment in our stomach. However, sometimes that pH balance is disrupted. Okay, some factors such as excess alcohol, smoking, caffeine, stress, and some anti-inflammatory drugs can cause excess production of this acidic secretion known as gastric juice. So when we take these other substances or smoke or have stress, some of the following problems can occur. So we could have acid indigestion, the feeling of discomfort from too much acid in the stomach. I'm sure you all have heard about heartburn or may have experienced it yourself. This is acid from the stomach rising into the esophagus, and this process is sometimes called acid reflux. Another potential problem is ulceration. So those lining of the stomach, sometimes damage is caused, resulting in loss of tissue and inflammation. The term dyspepsia is used to refer to feelings of pain and discomfort in the upper abdomen, which include indigestion and heartburn. Okay, so those are just a couple of examples of issues that could occur if that pH balance is not maintained. So how does this all work? Well, now we're going to get into what it actually looks like in our stomach. Okay, the body is equipped with complex mechanisms to protect it from the self-harm that could result from uncontrolled release of stomach acid. Together, these mechanisms ensure that gastric juice is released only when required. Okay, so for example, when we eat food, right, the stomach or these parietal cells release the hydrochloric acid that is required to break down the food that we eat. Several transmitters and chemical messengers called hormones are involved, and of these, one specific one is of specific interest, and that is histamine. Okay, so let's take a look at how this actually works. So histamine, which you can see a picture on the right, histamine has different functions in the body and several different receptor sites. So we're talking specifically about the stomach. So in the stomach, it stimulates secretion of stomach acid by interacting at receptors known as H2. But be aware, this is not hydrogen, okay, or hydrogen gas. They are called H2 receptors, and they are located in the parietal cells in the gastric glands. This histamine interaction initiates a sequence of events leading to the release of acid into the stomach lumen. This suggests that a possible target for a drug which will reduce stomach acid secretion would be to block the histamine H2 interaction. Drugs which do this and which compete with histamine for binding at the H2 receptors are known as H2 receptor antagonist. Okay, so there's a word that we saw previously, antagonist. So something, a drug, is going to interact with the H2 receptor and block the histamine. And then therefore, the parietal cell cannot secrete the acid. Okay, so let's take a look at some of those drugs that actually work this way. All right, the first one that we have is ranitidine, which is commonly known as Zantac. Okay, so Zantac is an example of an H2 receptor antagonist drug. It was developed from analogs of histamine, so it has a similar structure, using knowledge of the H2 receptor structure and refined from earlier drugs to increase its potency. In many countries, it is now available as an over-the-counter drug, but higher dosages need prescription. So if we go and take a look, that was the histamine. All right, you can see on the left-hand side the similar kind of structure to the Zantac. Okay, you probably have commonly heard of Zantac. It is also known as ranitidine. So, continuing on, let's actually dive down deep into what is going on. So, when the gastric acid is released into the stomach, okay, in the last step of this process, the parietal cells in the gastric glands will pump protons across their membranes and into the lumen of the stomach. For each hydrogen ion pumped into the lumen, one potassium ion is pumped in the opposite direction, so there is no charge buildup. Movement of the ions occurs against their concentration gradients and so requires energy. This is provided by the hydrolysis of an energy carrier known as ATP, using the enzyme ATPase, which is embedded in the cell membrane. Therefore, this specific enzyme is known as the hydrogen potassium ATPase, or simply as a gastric proton pump. Okay, so before we were dealing with one drug that was dealing specifically with the H2 receptors in the stomach. But now we have another possibility, and that is dealing with the proton pump or gastric proton pump. So the first proton pump inhibitor was a drug called omeprazole, and it was marketed as Prilosec. This was followed by the release of a similar drug, esomeprazole, or Nexium, when the patent for Prilosec expired in 2001. So here we can see the structures of our two drugs, Prilosec and Nexium. Okay, these are very, very similar, as you can see. So we now have two possible ways that we can affect the amount of hydrochloric acid that is released into our stomach. Okay, if you take a look at the first hand side, we have our histamine, which can interact with the H2 receptor. And then if we add a drug, our H2 receptor antagonist, such as ranitidine, it will block that receptor, and therefore the parietal cell will not release the gastric juice or the hydrochloric acid. The other way we can interact with the parietal cell is by using a proton pump inhibitor. Okay, this is, for example, omeprazole or esomeprazole, the Nexium or the Prilosec. Those interact with the proton pump, the hydrogen ion, potassium ion, and the ATPase, that is the enzyme. All right, so make sure you know how these two interactions are affected and which drugs can be used for which interaction. Now we're going to talk a little bit about antacids. Okay, antacids are also used to treat these conditions. Okay, when we have our stomach issues. Okay, they are weakly basic compounds that neutralize acids, thereby relieving the pain, discomfort, or burning sensation and allowing repair of the mucus layer. In the case of peptic ulcers, neutralization of the acid prevents further erosion of the gut lining, allowing ulcers to heal. So antacids are quite common, and the most commonly used antacids are metal hydroxides, carbonates, and hydrogen carbonates, also known as bicarbonates. Okay, so you have a couple listed there that you should be familiar with. Okay, we're going to be seeing those in some chemical reactions in a little bit. Now, one thing to note is some antacid preparations contain mixtures of two different antacids, such as a magnesium and aluminum compound. And the rationale for using these two different antacids is that magnesium salts are faster acting and so work quickly to neutralize the acid, but aluminum salts have a slower and more prolonged effect, so the time interval between doses is increased. Also, magnesium salts in repeated doses can cause a laxative effect, but this is offset by aluminum salts, which can induce constipation. Okay, so when we talk about antacids, sometimes it's not just one chemical that is used, it might be a mixture. So all of these antacids, which are slightly basic, will react with the hydrochloric acid. And if you remember, a base plus an acid, neutralization reaction, that gets you a salt plus water. So for the first three equations, they're all hydroxides. So we get salt plus water. For the last two, which are hydrogen carbonate and carbonates, okay, when they react, they will produce carbonic acid, which will automatically break down into a carbon dioxide and a water. So you could be asked to write equations for any of these. That's why you have to know how to write your formulas and know what type of reaction is occurring. Now we've talked a lot about side effects, so antacids, which are a drug, there are some side effects. So the gas release can cause bloating of the stomach and flatulence. To reduce this side effect, anti-foaming agents are often added to the formulation. Okay, an example is dimethicone. Some antacids also contain alginates, which oat to the top of the stomach, forming a raft which acts as a barrier, preventing reflux into the esophagus. And then note that because antacids change the pH of the stomach, they can alter other chemical reactions, including the absorption of other drugs. Although they are over-the-counter drugs, they should not be taken for an extended period of time without medical supervision. So let's take a look at what are known as active metabolites. Okay, these are the active forms of drugs after they have been processed in the body. Okay, we've talked about how some drugs contain the active form of the drug, and then some other components which might be broken down through the digestion process. So the previous lesson talked about codeine, right? Codeine is converted into morphine in the body, and it is the morphine that binds much more strongly to the opioid receptors than codeine, producing an analgesic effect. Okay, omeprazole and esomeprazole, which we just talked about, are converted into different forms that are able to bind to the proton pumps. And aspirin, which we've talked about previously, is converted into its active form, salicylic acid. Okay, salicylic acid, we talked about, cannot be taken orally because it causes severe irritation of the stomach lining, resulting in vomiting. Therefore, it is easier taken in ester form. This causes much less gastric irritation, but is converted back into the active analgesic in the body. Okay, so active metabolites are the active forms of the drug after they have been processed in the body. So why would we want to make a drug in a different form than its actually active metabolite? So a couple reasons. One, to avoid side effects, right? Aspirin has the vomiting and the effects on the stomach lining. Okay. Number two, we do this to allow the drug to pass through cell membranes. Right? For example, the active form of omeprazole is charged and would not pass through the cell membrane into the parietal cells. Diamorphine is another example that fits into this category. A third example would be to allow the drug to dissolve in water more easily. And finally, 4, to target drugs to a particular area. For example, omeprazole, where the active drug is formed only in the highly acidic conditions of the cells in the stomach lining. All right, so why don't we take a look at some practice questions? Why don't you go ahead and try to answer these on your own first, and then you can check the answers for these. Okay, number 13 says, suggest why the action of drugs in lowering the production of stomach acid is considered to be the indirect in the case of H2 receptor antagonists, but direct in the case of the gastric proton pump inhibitors. Okay, so we just talked about these two kind of ways in the parietal cells in the stomach. Okay, why is one indirect? Why is one direct? Okay, think about it for a second. Write down your answer. Well, H2 receptor antagonists, they block the binding of histamine, which prevents the reactions leading to stomach acid secretion, right? They are an antagonist, so they compete with another chemical in the body. Whereas in the case of the proton pump inhibitors, they work directly to prevent the release of acid into the stomach. Okay, two different drugs, both do the same result, but one is indirect, one is direct. Okay, number 14, magnesium hydroxide and aluminum hydroxide can act as antacids. Okay, write an equation for the reaction of hydrochloric acid with each of these antacids. Okay, you should be able to do that. Right, base plus acid, get to a salt plus water. Letter B says identify which antacid neutralizes the greater amount of acid if 0.1 moles of each antacid is used. Explain why potassium hydroxide is not used as an antacid. Okay, so let's start with letter B. Okay, we used 0.1 moles of each of these. Which one would neutralize the greater amount of acid? Well, in this case, you have to look at the balanced equations for each of these. Magnesium hydroxide reacts with 2 moles of hydrochloric acid, whereas aluminum hydroxide reacts with 3 moles of hydrochloric acid. So if you use the same amount of moles of your antacid, your base, well, the aluminum hydroxide will neutralize the greater amount, and that comes directly from the balanced chemical equation. Finally, letter C, explain why potassium hydroxide is not used as an antacid. Okay, potassium hydroxide was not on our list on the previous page. Okay, think about why that is. Well, potassium hydroxide is a strong alkali, so it would be dangerous for body cells. It is corrosive and it would upset the stomach pH, right? Potassium hydroxide, strong base, would dissociate completely, and that would affect the stomach pH. And that directly leads into our next lesson, which is on buffers. Okay, so we're going to go back to our acids and bases. If you do not remember what buffers are, you could take a look at that. A buffer solution is one that resists changes in pH when small amounts of acid or alkali are added. This is incredibly important in our body because our systems are very sensitive to changes in pH. So we have quite a number of buffers in our body. They want to prevent rapid, big or small changes in the pH. So one of the things you could be asked to do is to calculate when buffers are involved. Okay, so a buffer is going to deal with an equilibrium equation, so you should either have to write out the equation or it might be given to you. Okay, you're going to make some assumptions. The dissociation of the weak acid is so small that it can be considered to be negligible, and we're going to be dealing with a salt that fully dissociates into its ions. If we take those assumptions into account, then we can derive what is known as the Henderson-Hasselbalch equation to make these problems much easier. So the equations that I'm going to show you here are known as the Henderson-Hasselbalch equations. Okay, they are given in section 1 of the IB data booklet. If we know some information, we can then use it to calculate the pH of our buffer solution, taking into account the acid dissociation constant, or the base dissociation constant, that's Ka and Kb. And we'll need to know the ratio of initial concentrations of acid and salt used to prepare the buffer. Okay, so the equation that you need to know, usually you're going to be dealing with acids. So the first one you need to know, pH equals pKa plus a log of the concentration of the salt divided by the concentration of the acid. When we are dealing with a buffer solution, if you remember back when we dealt with acids and bases, the concentration of the acid is sometimes equal to the concentration of the salt. And if that happens, then pH is going to be equal to pKa. All right, so why don't we go ahead and actually try to practice using the Henderson-Hasselbalch equation. So the question is, calculate the pH of a buffer solution at 298 Kelvin prepared by mixing 25 cubic centimeters of 0.1 molar ethanoic acid with 25 cubic centimeters of 0.1 molar sodium ethanoate. The Ka of the ethanoic acid is 1.8 times 10 to the negative fifth at 298 Kelvin. Okay, so think about what we are given, what we know. Okay, and let's go ahead and try to solve this problem. All right, well, one of the parts of the Henderson-Hasselbalch equation is the pKa. That we are not given, but we are given the Ka. All right, so if we just take the negative log of the Ka, it can be converted into pKa. Now, taking this into account, that there are equal volumes and concentrations of our acid and our salt, right? 25 cubic centimeters of a 0.1 molar solution of both. Then the acid is equal to the salt. So if we plug in what we know, remember we're trying to solve for pH. Okay, there's the Henderson-Hasselbalch equation. pH equals pKa plus log concentration of the salt divided by the concentration of the acid. Then we plug in 4.74 plus log of 1. If you put log of 1 in your calculator, you get 0. So the overall pH of this solution is going to be 4.74. Okay, here's a problem I want you to think about. How would you prepare a buffer solution of pH 3.75 starting with methanoic acid and sodium hydroxide? Okay, sometimes you could be asked to make a specific pH solution. So we know we want our pH to be 3.75. We are given the acid, methanoic acid, and a strong base, sodium hydroxide. Well, if you remember, in order for a buffer to happen, we need a weak acid and a salt of its conjugate base. So since we need a pH of 3.75, we can look in the IB data booklet that the pKa of methanoic acid is indeed 3.75. So therefore, from the Henderson-Hasselbalch equation, we need to have equal amounts of our acid and our salt. So if we react the acid with enough sodium hydroxide so that 1/2 of the acid is converted into the salt, therefore the concentrations will be equal and they will cancel out. We'll get the log of 1, which is 0, so our pH is equal to our pKa. All right, continuing on. How much 0.1 molar butanoic acid solution and solid potassium butanoate should be used to make 1 molar, a 1 cubic decimeter, of pH 5.00 buffer solution? State the assumptions made in the calculation. Okay, so write down or underline the information that you know. Okay, we know the concentration of our acid. We know our volume of our solution. We need 1 cubic decimeter. And we know our pH. Okay, we want to get a pH of 5. Okay, we also know we're using butanoic acid, which means we can look in the data booklet to find the pKa. Okay, from all of that and from our Henderson-Hasselbalch equation, if we plug in what we know, we know our pH, we know our pKa, we know the concentration of our acid, but we do not know the concentration of our salt. Okay, in this case, we do not know the concentration of our butanoate ion. So if we plug in what we know, we plug in the pH, they have subtracted pKa to get that on the opposite side. So that is why you see 5 minus 4.83. Right? If you do that, that's equal to 0.17. And then we have this log. Hopefully you remember from your math class that to get rid of a log, you just take 10 to the power. So if we take 10 to the power on both sides, we know that 10 raised to the power of 0.17 equals the concentration of the butanoate ion divided by 0.1. Well, 10 to the 0.17 is equal to 1.5. From there, we can then solve for our concentration of our butanoate ion. Okay, you just multiply both sides by 0.1. So the concentration of our butanoate ion is equal to 0.15 molar. All right, we can find the molar mass of potassium butanoate. That's 126.12 grams per mole. Since we know the volume we need and we know the concentration, using the equation C equals N over V, okay, we can calculate the number of moles, which is 0.15 moles, multiply it by the molar mass, and that gets us to 19 grams of potassium butanoate. So 19 grams of this potassium butanoate should be added to 1 cubic decimeter of a 0.1 molar butanoic acid solution. Okay, the following assumptions were made: that at equilibrium, the initial concentration was equal to the equilibrium concentration for both the butanoate ion and the butanoic acid, and that no volume changes occur on mixing the solution. All right, we got one final problem. I want you all to try to do this on your own. Use your notes to try and figure this out. Look at the other practice problems. Do it on your own first before you try and do this by looking at the answer. Okay, 15A says that 100 cubic centimeters of a buffer is prepared which contains 0.1 molar butanoic acid and 0.200 molar sodium butanoate. What is the change in pH when 2 cubic centimeters of a 0.1 molar hydrochloric acid solution is added to this buffer. The pKa of butanoic acid is 4.82. All right, so let's first find out what our pH of, or what the pH of our buffer solution is. So we use the Henderson-Hasselbalch equation. pH equals pKa plus log concentration of the salt divided by the concentration of the acid. Okay, the pKa is given to us. The concentration of the salt is 0.020. We divide it by the concentration of the original butanoic acid, that is 0.010. Okay, remember, we're only using 100 cubic centimeters. That is why the concentrations in the equation are not equal to the concentrations given in the problem. When you do a little math, you get that the pH is equal to 5.12. Now, the question is actually asking, what is the change in pH when another amount of acid is added? Well, when you add 2 cubic centimeters of 0.1 molar 0.1 molar hydrochloric acid, you're adding an extra 2 times 10 to the negative 4th moles of acid. So that is why in the Henderson-Hasselbalch equation, you see 0.0102. That is the change. But by doing that, you can now see that with the small amount of acid, the pH has gone down, which is expected, to 5.11. It's not a dramatic change, and this is the point of a buffer. And last but not least, letter B. How would the pH of the buffer alter if 20 cubic centimeters of distilled water was added to the original solution? Okay, so if we added some water, would that affect the pH? The answer is no. Buffer solutions do not change pH on dilution, only when we add acids or bases.